Hello everyone, welcome to my presentation. My name is Yousef Heider, and I'm a research associate at the RWTH Aachen University in Germany. I will give today a presentation with the title, A Numerical and Experimental Study of Porous Media Phase Field Fracture. This topic is very important in many fields of engineering, especially in geothermal and petroleum engineering, in soil science, and in geomechanics. Take, for instance, from the field of geothermal energy, the case of enhanced geothermal system. In this case, we have layers of rocks with naturally have very low permeability. Using the hydraulic fracturing technology, it helps us to increase the permeability of these layers, and as a result, we get enhancement and more efficient systems. The other examples from soil science, in this case, the drying of soil, in this case it would be maybe clay or clay soils. It leads to such a fancy patterns of cracking networks, and this is a very important topic. And the third topic would be the slope stability. So due to rainfall or to drying, there are some changing in the water table, and this leads to changing in the hydromechanical properties of soil layers, and this might lead also to collapse and kind of fracturing. So this is also an important topic to be addressed. So the aim in this presentation is to understand and predict the onset of porous media fracture. This can be done using numerical models. And we would like also to calibrate our model and validate this model also by conversion with experimental data, either from the literature or our own data. And the method which we are following is that we are applying continuum mechanical modeling of this multi-phase material, and we apply for the fracture modeling the phase field method. And at the end of this presentation, I will talk a little bit about the future aspects and possible extension towards inclusion of machine learning-based material models. So after this short introduction, I will talk very briefly about the phase field modeling approach and also the continuum modeling of unsaturated porous media. And then there will be two examples, one related to drying induced fracture and one is related to hydraulic fracturing, and at the end are the future works. So very roughly, the phase field modeling of fracture is based on the idea of approximating the sharp cracks of brittle materials. So brittle materials will break in a very sharp crack interface. This can be approximated by diffusive one. In this case, the crack surface, which is not anymore like a line or surface integration, but it would be like volume integration. And this can be done relying on the function gamma, which is called the crack density function. For this, we need a phenomenological phase field variable. We call this D. It's a scalar value, and it has a value of 1 if we have a crack, 0 if we have intact material, and it will be between 0 and 1 in the interface. This approach allows us to approximate the diffuse fracture energy and to write it in this form. In this case, the GC would be the Griff's critical fracture energy, and multiplied by our function gamma. And in this formulation, you see we have a new material or model parameter. It's called LC, and it is an internal length scale. This parameter controls the width of the diffusive interface. And if we want to model a brittle fracture, we need to choose this parameter very small, or we have to give it a very small value, and then we have to also refine our mesh according to these values. Now for the porous media, which is unsaturated, the continuum approach starts in a kind of standard way. So first we choose a representative volume element, and this consists of 3 phases. We have the solid phase, the liquid or water phase, and the air phase. So 3 phases, then we apply homogenization. In the homogenized material, we have at each material point 3 phases, the gas, the liquid, and the solid, and they are overlapping and interacting. And from this, we define also the volume fractions, n, and the sum of volume fractions of the three phases equal to 1. This is a restriction, and this has always to be valid in the modeling. As we are talking about unsaturated porous media, we have additionally the degree of saturation. And this is given in terms of the effective value and the residual saturations. So, in reality, you cannot get like completely dried or completely saturated material. There should be some residual of the either gas or water. So we based on this, we define this relationship. And a constitutive model related to unsaturated porous media is the retention curve, which is a relationship between the degree of saturation and the suction or the capillary pressure, PC, which is a gas pressure minus liquid pressure. There are in the literature many models to describe this retention behavior, and we choose one of the popular models, which is the Frank-Nuchten model. It's given in this equation, and it needs like 5 material parameters to be determined. 3 are here, and 2 additional related to the relative permeabilities, and it's given in terms of the static pressure head, which is an output of the modeling. And the second material model is a Bischoff's effective stress, and this is the total stress equals to the effective one minus pressure term, and this pressure term includes the gas pressure and the liquid pressure. By some reformulation, we see that we get in this effective stress relationship, we get the suction or the capillary pressure, in addition to a parameter xi, which is in Bischoff's approach, it's approximately equal to the degree of water saturation. And this is what we are implementing, or this is what we are like considering in our model. Now we come to the phase field fracture, and its inclusion in the porous media approach. The basic idea is that when we have a crack, then we have degradation in the stiffness. That's why we start by defining the degradation function, G of D. It's mainly a function of the phase field variable D. And we include additionally like a parameter eta, which is like residual stiffness. It's needed only for some numerical stability issues. But if we want to consider like completely broken material, then this eta should be 0. So we multiply this degradation function by what we call positive energy. So the positive energy would include the tensile stresses and the shear stresses. In addition to this, in unsaturated porous media, we will have the additional contribution due to the suction. So this also have to be degraded. And then the total energy would also include the fracture energy, as we discussed before. Based on this, we can like derive our stress tensor. So the stress would be simply the derivation of the energy with respect to the strain. And then we get this first relationship of the stress, which is in connection with the drying induced fracturing. You see that the degradation function is multiplied by the elastic energy, which is like the positive one, and also includes the contribution of the suction. So PG minus PL. It means that when we have a crack, as in the illustrated figure, the liquid bridges will also be broken, and then we'll have no suction anymore. So this also has to be degraded. If we have wetting or hydraulic fracturing due to the injection of fluid in a certain domain, then the suction does not really play a very important role. In this case, the degradation function will be multiplied by the elastic energy contribution to the stress. So would be this is a positive value, which is as I said, the tensile and the shear stress. And this is for hydraulic fracturing. It's exactly the same relationship if we consider one phase fluid. So unsaturated would be 2-phase, and fully saturated would be single-phase fluid. The fracturing in porous media, and if we have a fluid flowing, so it leads to changing in the hydraulic properties of our material. That's why it's important to address the issue of permeability change due to the crack. So previously or initially, when you have no crack, so the permeability of the material is almost isotropic. So it has the same value in all directions. So when we have a crack opening, the flow in the crack direction will be enhanced. So we have a kind of anisotropic permeability, and this can be expressed in this relationship, which is written here. It's a function of WH, which is the crack width. This can also be determined based on the gradient of the phase field variable and also based on the local deformation of the material. So with this, we include in our model the isotropic and the anisotropic permeability. There are a number of additional extensions, like the residual saturation would be different in the crack. So the cracks, there will be like the almost no residual saturations, and this can also be considered in the model. So at the end of the day, we will have a number of partial differential equations which govern the behavior of our material. In particular, if we consider isothermal states, so we have 4 equations, which are the overall momentum balance, the liquid mass balance, the gas mass balance, and the phase field evolution equation. So in this case, in the numerical simulation, we have to deal with a strongly coupled problem with 4 primary variables, which are the solid displacement, the pressure, the liquid pressure, the gas pressure, and the phase field variable. If we are dealing with finite element methods, then this problem, especially in the porous media problem, it represents a twofold, or we have to fulfill the twofold if sub condition. And if we use like equal order shape functions, then we have to use also a stabilizing term, especially if the permeability tends to be very low, or the fluid becomes very almost incompressible. So we have to take care of the instability sources. And in our treatment, we applied this staggered solution scheme, in which we started by computing the crack deriving force, and then we solved the phase field equation in an implicit way using the second order backward difference formula. And then when we get the phase field variable, then we solve the unsaturated porous media problem in a kind of monolithic way. And at the end, we check the convergence, and we make sure that our errors are in the limits which we assigned at the beginning of the analysis. Let's present one of the examples, the drying induced fracture. So we have this domain, it's unsaturated clay, and we apply the drying process on this. Here, as I said, we have no temperature, so the drying would be kind of out of flux at the boundary. It's by the flux vector QW. And so initially we have no capillary pressure, and the residual saturations are 15%. So when the drying process starts, we see that the cracking starts to propagate at the beginning from the bottom and then from the top, and then we get like different cracks propagating at different speeds and so on. In the analysis, we tested a number of issues: material parameters, different boundary conditions, model parameters, how all these issues affect the cracking patterns. And as for instance, here the permeability is a very important factor. So once we go towards very high permeability, then we will not have a lot of cracks, or maybe no cracks at all. And if we have very low permeability, just like clay, then we'll have more cracks. So it's as you see here in this picture, you have a lot of cracks. The second example is related to hydraulic fracturing. So this is the opposite process. Here we inject fluid in the domain, and we had a number of experiments in our institution. So we had this triaxial testing machine, in which we have a sample of rock in the middle of this machine, and it's subject to confining stresses. This sample, it has a well bore and in the middle of this sample we are injecting fluid. Our choice is a glycerol. It's a highly viscous fluid, and the reason for this choice was this highly viscous fluid, it leads to kind of stable crack propagating process. This fluid was also mixed with some colors in order to determine the radius of our crack. And this is like a illustration of the model. It's the 2D, but we have also 3D. It shows the stresses at the boundaries and the mesh refinement. We refined the mesh at the beginning in the location where we expect our crack to be propagated. So we have two models. The first model is with fully saturated porous media, but the fluid is compressible as we have dissolved air bubbles. And the second model is unsaturated porous media, where we have gas and liquid phases. This is an illustration of how the crack propagation look like in our 3D model. So its first impression is qualitatively we are getting very comparable results with our experiment. And this is a first comparison with the experiment. So we tested our model for different experiments. So this is one of them. You see the red line represents the fluid volume flux, and it's changing by the time. We assigned exactly the same flux in our model. And then we are looking at the black and the blue curves, which represent the pressure time history. They have the same tendency, and if we look at the maximum pressure needed to initiate the crack, we see that our model can approximate this value by an error of almost 8%. Also, the crack radius is comparable with the experiment with an error of 5%. We tested a number of cases. This is another case where we have different volume flux, and we are seeing that we are getting again comparable results. So this shows that our model is actually capable of modeling this process, although it's very complicated. The second example is we assume that our material is unsaturated with initial saturation of 40% in the domain and 99% in the notch. And then after the crack, we see that inside the crack we have like negative air pressure, which this is what we actually expect, because then we have suction towards the crack, and this is what can be observed in the reality. And the fluid pressure around the crack is higher than inside the crack. This was an interesting finding. And of course, the degree of saturation inside the crack would be almost 100%. This is logical. We have a number of future worse aspects, and I will address one of them here. It's about improving the accuracy of our model. What we are doing here is we are using machine learning approaches to generate material models. We have a number of material models in unsaturated porous media. One important one is the retention curve, and this can be generated using multi-scale modeling. And the first step would be then to generate a database for our machine learning model. And this database, we use to generate the discrete element method for the deformation of our porous material, and the Lutz-Boltzmann method in order to generate the permeability and also the retention curve. So we get a relationship or a database which includes the suction, BC, the porosity, and the degree of saturation. From this, we take this database and we put this in our machine learning algorithm. The retention curve is path dependent. We distinguish between drying and wetting processes. So we use a recurrent neural network to generate our model. And then we can test our model if we really can capture this behavior. We test this on unseen data, so the data which is not a part of the training. And then if it shows a very good performance, then we implement this in our finite element model as a replacement of the conventional or the phenomenological retention curve model. So This is like the presentation. I would like to acknowledge the support and funding of the RWTH Aachen University in Germany and the Columbia University in the US, where I did the research work on this topic. Particularly, I would like to thank Professor Bernd Market and Professor Weiching Sun for their useful and important discussion and their support. And with this, I'm at the end of my presentation. Thank you very much for your attention, and have a very nice day. Thank you.